Introduction to Kerberos Authentication. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Kerberos is a network authentication protocol that was developed at MIT in the 1980s and has become the foundation of modern enterprise authentication systems. The name Kerberos comes from Greek mythology, referring to the three-headed dog that guards the gates of Hades. This is fitting because the protocol involves three main parties in its authentication process: the client who wants access, the service the client wants to use, and the trusted third party that vouches for everyone's identity. What makes Kerberos particularly powerful is that it never transmits passwords across the network. Instead, it uses a sophisticated system of encrypted tickets that prove identity without ever exposing credentials. This approach solves a fundamental problem in network security. How do you verify someone's identity without them having to send their password to every service they want to use? In traditional authentication, if you wanted to access 10 different services, you might need to send your password 10 times, creating 10 opportunities for interception. Kerberos eliminates this risk entirely. The protocol is built on symmetric key cryptography, which means both parties in a conversation share a secret key. However, Kerberos cleverly arranges these shared secrets so that clients and services do not need to directly exchange keys with each other. Instead, they both trust a central authority called the Key Distribution Center, or KDC. The KDC acts as a trusted intermediary that can vouch for identities and facilitate secure communication between parties that have never directly exchanged credentials. In modern Windows Active Directory environments, Kerberos is the default authentication protocol. When you log into your workstation in the morning, open your email, access a file share, or connect to a database, Kerberos is working behind the scenes to authenticate you. The protocol operates transparently, requiring no user intervention beyond the initial login. This single sign-on capability means users authenticate once at the beginning of their session and can then access multiple services without repeatedly entering credentials. Kerberos realms and domains. In Kerberos terminology, a realm is an administrative authentication domain that defines the scope of the KDC's authority. Every principal, whether a user or service, belongs to a realm. The realm name is typically represented in uppercase letters and often corresponds to a DNS domain name. For example, if your organization's domain is example.com, the Kerberos realm would be example.com. This distinction between lowercase DNS names and uppercase realm names is a convention that helps distinguish between DNS operations and Kerberos authentication operations. In Windows Active Directory environments, the realm directly corresponds to the Active Directory domain. For example, if you have a domain named corp.contoso.com, the Kerberos realm is corp.contoso.com. This tight integration makes Kerberos authentication seamless in Windows environments. The domain controller serves as the KDC, and all authentication requests for that domain are handled by that KDC. If you have multiple domain controllers in a domain, they all function as KDCs, providing redundancy and load distribution for authentication requests. One of the powerful features of Kerberos is its support for cross-realm authentication. When you have multiple domains or organizations that need to trust each other, Kerberos can establish trust relationships between realms. In Active Directory, this is implemented through domain trusts. When a user from one domain needs to access a resource in another domain, Kerberos can chain authentication requests across the trust path. The user's home KDC issues a special inter-realm TGT that allows the user to authenticate to the foreign realm's KDC, which then issues tickets for services in that realm. The concept of realms is important because it defines the boundary of authentication authority. Each realm has its own KDC, its own database of principals, and its own set of cryptographic keys. A principal's full name in Kerberos includes the realm, written as user@realm.com. This fully qualified name is globally unique across all realms and clearly indicates which KDC has authority over that principal. Services are identified similarly with their service principal names, which include the service type, hostname, and realm. Ticket structure and components. A Kerberos ticket is an encrypted data structure that serves as a credential proving ID and granting access. Understanding the internal structure of tickets is crucial to understanding how Kerberos achieves its security properties. A ticket contains several critical pieces of information, all encrypted to prevent tampering and eavesdropping. A ticket's outermost structure includes its encryption type and the encrypted data blob. The encryption type field indicates the algorithm used to encrypt the ticket. For example, AES-256, CTS, HMAC, SHA-1, 96. This tells the recipient which key and algorithm to use for decryption. The encrypted portion contains the actual ticket data, which then includes several key components. First, the ticket contains the client's principal name, which identifies who the ticket was issued to. This is the fully qualified name, including the realm, like user@example.com. This ensures that tickets cannot be stolen and used by a different principal. Second, the ticket contains the service principal name, which identifies what service this ticket grants access to. For a TGT, the service principal is the TGS itself, usually Kerb TGT at realm.com. For a service ticket, it is the specific service being accessed, like http://webserver.example.com at example.com. The ticket includes a session key, which is a randomly generated encryption key specific to this ticket. This session key will be used by the client and service to encrypt their communications. The client receives a copy of this session key in the encrypted portion of the KDC's response, while the service receives it inside the encrypted ticket. This means the session key is shared between client and service without ever being transmitted in a form that a network eavesdropper could read. Timestamps are critical security components in Kerberos tickets. Each ticket contains a start time indicating when it becomes valid, an end time indicating when it expires, and optionally a renew until time for renewable tickets. The start time prevents pre-dated tickets. The end time limits the window of vulnerability if a ticket is compromised, and the renew until time controls how long a ticket can be extended. Additionally, the ticket contains an authentication timestamp from when the client originally authenticated, which helps prevent replay attacks. The ticket also includes authorization data, which in Active Directory contains the client's security identifiers and group memberships. This authorization data is used by Windows services to make access control decisions based on group membership and privileges. The authorization data is also encrypted and integrity protected, ensuring that an attacker cannot modify group memberships to gain unauthorized access. Finally, the ticket includes flags that control its behavior, such as whether it's forwardable, proxyable, renewable, or marked as requiring pre-authentication. Authentication Service Response-ASREP. When the KDC receives the ASREQ message, it performs several validation checks before issuing a response. The KDC looks up the client principal in its database to retrieve the client's long-term key. It then uses this key to decrypt the pre-authentication data. If decryption succeeds and the timestamp is current within the allowed clock skew window, typically 5 minutes, the KDC knows the client possesses the correct password. The KDC also checks that the client account is enabled, not expired, and not locked out due to failed authentication attempts. If all validation checks pass, the KDC constructs an Authentication Service Response, or ASREP. The ASREP contains two main encrypted components. The first component is encrypted with the client's long-term key and contains information meant only for the client. This includes a session key that will be used for subsequent communications with the TGS. The session key is a randomly generated symmetric key, completely independent of any passwords or long-term keys. The encrypted portion also includes the ticket's lifetime information, showing when it becomes valid and when it expires, along with other metadata about the ticket. The second component of the AS-REP is the ticket granting ticket itself, which is encrypted with the TGSS long-term key. This is the key belonging to the Kerb TGT account. The TGT is encrypted so that only the TGS can decrypt it. The client cannot read the contents of their own TGT. Inside the encrypted TGT is another copy of the session key, matching the one sent to the client. The TGT also contains the client's principal name, the service principal name of the TGS, timestamps indicating validity period, and authorization data such as the user's group memberships and security identifiers. When the client receives the AS-REP, it immediately uses its long-term key to decrypt the first portion and extract the session key. This session key is stored in the client's credential cache. The client also stores the encrypted TGT in its cache but cannot, and does not need to, decrypt it. The TGT will be sent back to the KDC in future requests, where the TGS service will decrypt it. From this point forward, the client has everything needed to request access to services. The initial authentication is complete, and the client does not need to use its password again until the TGT expires or the user logs out. The use of 2 layers of encryption in the AS-REP is crucial to Kerberos security. By encrypting the TGT with the TGS key rather than the client key, Kerberos prevents the client from tampering with the contents of the TGT. If the TGT were encrypted with the client key, a malicious user could decrypt it, modify the authorization data to add themselves to administrative groups, re-encrypt it, and then use it to gain unauthorized access. By keeping the TGT encrypted with a key known only to the KDC, the system ensures that the TGT contents remain tamper-proof. The client can present the TGT but cannot forge or modify one. Ticket Granting Service Response (TGSREP). Once the KDC validates the TGS request and authorizes the client to receive a ticket for the requested service, it then creates a TGS rep message. The structure of the TGS rep is similar to the AS rep but serves a different purpose. Instead of providing a TGT for general use, the TGS rep provides a service ticket for accessing one specific service. The TGS rep contains 2 encrypted components. The first is encrypted with the session key from the TGT, the same key the client used to encrypt the authenticator. This encrypted portion contains a new session key specifically for communicating with the target service. This new session key is independent of the TGT session key, providing isolation between different service requests. The encrypted portion also includes timing information about the service ticket and other metadata such as the service principal name and ticket flags. The second component is the service ticket itself, which is encrypted with the service's long-term key. This key is derived from the password of the account under which the service runs. In Active Directory, services typically run under either a computer account or a managed service account, both of which have associated passwords and encryption keys. The encrypted service ticket contains several key pieces of information: the new session key, the client's principal name, authorization data such as group memberships, timestamps defining its validity period, and various flags that control the ticket's properties. When the client receives the TGSREP, it uses the session key from its TGT to decrypt the first portion and extract the new service session key. The client caches both this session key and the encrypted service ticket. The client still cannot decrypt the service ticket itself. Only the target service can do that. This encrypted service ticket is what the client will present to the service when attempting to access it. The ticket acts as a tamper-proof credential issued by a trusted authority, the KDC, vouching for the client's identity. The TGS can issue service tickets for any service in the realm as long as the service is registered in the KDC's database and has an associated service principal name. In Active Directory, SPNs are registered as attributes on user or computer account objects. When you install a service like SQL Server, the installer typically registers the appropriate SPNs automatically. If SPNs are missing or incorrectly configured, Kerberos authentication will fail, and the system may fall back to NTLM authentication, which is less secure and doesn't provide the same single sign-on capabilities. Client Service Authentication, APREQ. The final exchange in the Kerberos authentication process occurs between the client and the service itself. This is called the Application Request and Response Exchange, or APREQ and APREP. At this point, the client has a service ticket encrypted with the service's key and a session key for communicating with the service. The client is now ready to authenticate to the service and begin using it. The client constructs an APREQ message containing two main components. The first component is the encrypted service ticket obtained from the TGS. The client includes this ticket in its entirety without modification, since the client cannot decrypt or read its contents. The second component is an authenticator, similar to the one used in the TGS REQ but encrypted with the service session key rather than the TGT session key. This authenticator contains the client's principal name, a current timestamp, and optionally a subkey that can be used for encrypting application data. When the service receives the APREQ, it performs its own validation process. First, the service uses its long-term key to decrypt the service ticket. This reveals the session key that was generated by the TGS specifically for this client service session. The service then uses this session key to decrypt the authenticator. If decryption succeeds, the service knows the client possesses the correct session key, proving they are the legitimate recipient of the service ticket. The service verifies that the client name in the authenticator matches the client name in the service ticket and checks that the timestamp is current and hasn't been seen before. At this point, mutual authentication may occur if requested by the client. In mutual authentication, the service proves its identity back to the client, ensuring the client is not communicating with an imposter service. The service constructs an APREP message containing a timestamp encrypted with the session key. Only the real service, which possesses the correct long-term key to decrypt the service ticket and extract the session key, can create a valid APREP. When the client receives and successfully decrypts the APREP, it knows the service is legitimate. After successful authentication, the client and service can communicate securely using the session key. They can encrypt and integrity protect their application data using this key. The session key provides confidentiality and integrity for the communication channel. This is particularly important for protocols that do not have their own encryption layer. For example, when accessing a CIFS file share over the network, the file data can be encrypted using the Kerberos session key to prevent eavesdropping. The session key remains valid for the lifetime of the service ticket, after which the client would need to obtain a new ticket to continue accessing the service. Complete authentication flow overview. Now that we've examined each individual exchange in detail, let's step back and look at the complete Kerberos authentication flow from start to finish. Understanding how all the pieces fit together is crucial to appreciating the elegance and security of the protocol. The entire process involves three main phases: initial authentication to obtain a TGT, requesting a service ticket, and finally authenticating to the service itself. The process begins when a user logs into their workstation. The user enters their username and password, which never leave the local machine. The client software derives an encryption key from the password and then constructs an ASREQ message that contains an encrypted timestamp. This message is sent to the authentication service component of the KDC. The AS validates the request by decrypting the timestamp and checking that it is current. If validation succeeds, the AS generates a random session key and constructs two encrypted packages. One package is for the client, containing the session key. The other is for the TGS, containing a TGT with that same session key embedded inside. When the client receives the AS rep, It decrypts the client portion to extract the session key and stores both the session key and the encrypted TGT in its credential cache. At this point, the initial authentication is complete. The user is now logged in, and the client has the credentials needed to request access to services. This entire AS exchange typically happens once per logon session, and the TGT remains valid for a configured lifetime, typically 10 hours in Active Directory environments. The second phase begins when the user attempts to access a network resource. For example, the user might open File Explorer and navigate to a network share. The client retrieves the TGT from its cache and constructs a TGSREQ message requesting a ticket for the file service. This message includes the encrypted TGT and a new authenticator encrypted with the TGT session key. The TGS validates the request by decrypting the TGT to extract the session key, and then using that session key to decrypt the authenticator. If everything checks out, the TGS generates a new session key specific to the file service and issues a TGSREP containing this new session key and a service ticket. The final phase involves the client authenticating directly to the service. The client creates an APREQ message containing the service ticket and an authenticator encrypted with the service session key. When the file server receives this message, it decrypts the service ticket with its own long-term key, extracts the service session key, and uses it to decrypt the authenticator. If validation succeeds, the service grants access. At this point, the client and service can communicate securely using the service session key. The beauty of this design is that after the initial TGT is obtained, the user can access many different services without the KDC being involved in every single access. The client can cache service tickets and reuse them until they expire, reducing network traffic and KDC load. Service Principal Names (SPNs). Service Principal Names, or SPNs, are a critical component of Kerberos authentication in Active Directory. An SPN is a unique identifier for a service instance running on a server. When a client wants to authenticate to a service using Kerberos, it needs to know the service's SPN so it can request the correct service ticket from the KDC. Understanding SPNs is essential for troubleshooting Kerberos authentication issues. An SPN has a specific format: service class/host:/port/service name. The service class identifies the type of service, such as HTTP for web services, MS SQL for SQL Server, or CIFS for file services. The host is the fully qualified domain name of the server running the service. The port is optional and only needed if the service runs on a non-standard port. The service name is also optional and used when multiple instances of the same service type run on the same host. For example, an SPN for a web server might be http:/webserver.corp.contoso.com, while an SPN for SQL Server might be mssql/sqlserver.corp.contoso.com:1433. SPNs are registered as attributes on account objects in Active Directory. For services running under the computer's local system account or network service account, the SPN is registered on the computer account object. For services running under a domain user account or managed service account, the SPN is registered on that user account object. When a service is installed, the installer should automatically register the appropriate SPNs. However, SPNs can also be manually registered using the setSPN.exe command line tool. When a client needs to access a service, it constructs the SPN based on the service type and the server name it's connecting to. For example, if you type FileServer share in Windows Explorer, the client constructs the SPN CIFS/fileserver.corp.contoso.com and sends a TGSREQ to the KDC requesting a ticket for that SPN. The KDC looks up the SPN in its database to find which account the service runs under, retrieves that account's long-term key, and uses it to encrypt the service ticket. When the client presents the ticket to the service can decrypt it because it has the same long-term key. Common issues with SPNs include duplicate SPNs and missing SPNs. If an SPN is registered on multiple accounts, the KDC does not know which account's key to use for encrypting the service ticket, and authentication will fail. If an SPN is missing entirely, the KDC cannot find the service, and authentication will fail, often causing the system to fall back to NTLM authentication. You can query SPNs using setSPN with the Q or L flags. For example, setSPN Q http://webserver.corp.contoso.com will query for that specific SPN and show which account it is registered to. Proper SPN management is crucial for maintaining Kerberos authentication in Active Directory environments. Service for User (S4U) extensions. The Service for User extensions, commonly abbreviated as S4U, are important protocol extensions that enhance Kerberos delegation capabilities. There are two S4U extensions: S4U2 Self and S4U2 Proxy. These extensions enable scenarios that were not possible with the original Kerberos protocol, particularly around delegation and handling users who authenticate through non-Kerberos mechanisms. S4U2 Self, also known as Service for User to Self, allows a service to obtain a service ticket to itself on behalf of a user. This might seem circular, but it solves a critical problem. What happens when a user authenticates to a service using a non-Kerberos mechanism like forms-based authentication, certificate-based authentication, or NTLM? In these cases, the service receives credentials or proof of identity, but it doesn't have a Kerberos ticket for the user. With S4U2 Self, the service can request a service ticket from the KDC on behalf of the user, using just the user's principal name. The KDC issues a forwardable service ticket for the service itself, which the service can then use with S4U2 Proxy to obtain tickets to back-end services. The S4U2 Self process works in the following way. The service authenticates to the KDC using its own credentials, and sends a TGS request that includes the user's principal name in a special PA for user field. The service is essentially saying, I have authenticated this user through some other means, and I need a Kerberos ticket for them. The KDC validates that the service account is trusted for delegation, and issues a service ticket to the requesting service with the specified user as the client principal. This ticket can then be used for further delegation through S4U2 Proxy. This is particularly useful for web applications that use forms authentication or external identity providers, but need to access back-end Windows services with the user's identity. S4U2 Proxy, also known as Service for User to Proxy, is the mechanism that implements constrained delegation. It allows a service to request a service ticket for another service on behalf of a user, using evidence that the user authenticated to the first service. The evidence is typically either a forwardable service ticket that the user presented during authentication, or a ticket obtained through S4U2 Self. When the service needs to access a back-end resource, it sends a TGS REQ to the KDC that includes the evidence ticket and requests a ticket for the target service. The KDC validates several conditions before issuing the delegated ticket. First, it checks that the requesting service account is configured for delegation to the target service, either through constrained delegation or resource-based constrained delegation. Second, it verifies that the evidence ticket is valid and forwardable. Third, it checks that the user account is not marked as sensitive and cannot be delegated, which is a protection for high-privilege accounts. If all checks pass, the KDC issues a service ticket for the target service with the original user as the client principal but marked with a forwarded flag indicating it was obtained through delegation. The target service can then check this flag and apply any delegation-specific policies. Clock skew and time synchronization. Time synchronization is absolutely critical for Kerberos to function properly. The protocol uses timestamps extensively to prevent replay attacks and to define ticket validity periods. If the clocks on the client, service, and KDC are not synchronized within an acceptable tolerance, authentication will fail. Understanding how Kerberos handles time and the importance of clock synchronization is essential for maintaining a healthy Kerberos environment. Kerberos uses timestamps in multiple ways throughout the authentication process. In the ASREQ, the pre-authentication data contains a timestamp that the KDC checks to ensure the request is current. In authenticators sent with TGSREQ and APREQ messages, timestamps prove that the client possesses the session key and that the message is fresh, not a replay of an old message. Tickets themselves contain start times and end times that define their validity period. All of these timestamp checks depend on the clocks being reasonably synchronized. The tolerance for clock skew in Kerberos is configurable, but it has a default value of 5 minutes in most implementations, including Active Directory. This means if the time difference between a client and the KDC exceeds 5 minutes, authentication will fail with an error message indicating that the clock skew is too great. The same principle applies between a client and a service. When the KDC receives an ASREQ, it decrypts the pre-authentication timestamp and compares it to its own current time. If that difference exceeds the configured maximum clock skew, the request is rejected. Similarly, when a service receives an APREQ with an authenticator, it checks the timestamp against its local time. In Active Directory environments, time synchronization is handled by the Windows Time Service, or W32 Time. The domain controllers maintain authoritative time, with the PDC emulator role holder acting as the authoritative time server for the domain. Domain controllers synchronize their time with the PDC emulator, and member servers and workstations synchronize with domain controllers. This hierarchical time synchronization ensures that all systems in the domain maintain synchronized clocks within the acceptable tolerance. The PDC emulator itself should be configured to synchronize with an external reliable time source, such as NTP servers on the Internet, or GPS-based time servers. Time synchronization issues are a common cause of Kerberos authentication failures. If a workstation's clock drifts out of sync, users on that workstation will be unable to authenticate. If a domain controller's clock is wrong, it might reject valid authentication requests or issue tickets that other services reject. Monitoring time synchronization across your environment is crucial. You can check time synchronization status using the W32TM command line tool. For example, W32TM/query/status shows the current time source and synchronization state, while W32TM/strip-chart/computer domain controller monitors the time offset from a specific domain controller. Maintaining proper time synchronization requires ensuring that the Windows Time Service is running on all systems, that firewall rules allow NTP traffic, and that external time sources are reachable. In virtual environments, you must carefully configure time synchronization between the hypervisor and guest operating systems to prevent clock drift. Golden ticket and silver ticket attacks. Golden ticket and silver ticket attacks are advanced techniques that exploit stolen credentials to forge Kerberos tickets. These attacks represent complete compromise scenarios where an attacker has obtained critical cryptographic material and can create arbitrary tickets. Understanding these attacks and how to detect them is essential for security teams managing Active Directory environments. A golden ticket attack occurs when an attacker obtains the password hash of the KRBTGT account. The KRBTGT account is a special built-in account in every Active Directory domain whose password hash is used to encrypt and sign all TGTs issued by the domain controllers. If an attacker obtains this hash, they can forge TGTs for any user, including non-existent users, and assign arbitrary group memberships and privileges. These forged TGTs are cryptographically valid because they are encrypted with the correct key, so the KDC accepts them as legitimate. With a golden ticket, an attacker has complete control over authentication in the domain and can maintain persistent access even if all other compromised accounts are remediated. Golden tickets are created using tools like Mimikits, which can extract the TGT hash from memory on a domain controller or from the ntds.did database file. Once created, a golden ticket can be injected into the attacker's session, allowing them to authenticate as any user. The tickets can be created with very long lifetimes, potentially years, though extremely long lifetimes may be more easily detected. Golden tickets bypass normal authentication and auditing, as the attacker doesn't need to contact the domain controller for authentication. They simply present their forged TGT to the TGS when requesting service tickets. Detecting golden ticket attacks is challenging because the forged tickets are cryptographically valid. However, there are some indicators. First, monitor for unusual ticket lifetimes. If a ticket claims to be valid for an unrealistic duration, it may be forged. Second, look for tickets that include suspicious group memberships or SID history entries. Third, watch for authentication events that don't have corresponding ASREQ events in the logs, indicating a ticket was used without initial authentication. Fourth, monitor for tickets used from unusual IP addresses or locations. The most effective defense against golden tickets is prevention. Protect domain controllers with extreme security measures, limit who can access them, implement credential guard, and regularly rotate the KERB-TGT password. Microsoft provides a script called the KERB-TGT Privileged Account Maintenance Rotation Script to safely rotate the KERB-TGT password. Silver ticket attacks are similar to golden tickets but target individual services instead of the entire domain. In a silver ticket attack, the attacker obtains the password hash of a service account and uses it to forge service tickets for that specific service. Unlike golden tickets, which allow the attacker to obtain tickets for any service, silver tickets only grant access to the compromised service. However, silver tickets are even harder to detect. This is because they do not require interaction with the KDC. The attacker forges the service ticket directly and presents it to the service. The service validates the ticket using its own key, which the attacker also possesses, so it accepts the forged ticket as valid. Defending against silver ticket attacks requires protecting service account credentials. Use managed service accounts or group managed service accounts, which have long, complex passwords that change automatically. For regular service accounts, enforce strong password policies and regular rotation. Monitor for unusual authentication patterns to services, particularly access outside normal business hours or from unusual locations. Implement strong auditing on sensitive services so that access events are logged even when authentication succeeds. Finally, apply the principle of least privilege to service accounts and regularly review their permissions to ensure they haven't accumulated excessive privileges over time. Troubleshooting Kerberos authentication. When Kerberos authentication fails, it can be challenging to diagnose the root cause because the protocol involves multiple components and various encryption layers. However, understanding common failure scenarios and having the right troubleshooting tools can help you quickly identify and resolve issues. Let's explore the systematic approach to troubleshooting Kerberos problems. The first step in troubleshooting is to verify basic network connectivity. Kerberos requires that clients can communicate with domain controllers on specific ports. UDP and TCP port 88 are used for Kerberos authentication requests. UDP and TCP port 389 are used for LDAP queries to look up SPNs and account information. Port 53 is needed for DNS resolution. If firewalls block these ports, Kerberos authentication will fail, and the system may fall back to NTLM or fail entirely. You can test connectivity using Telnet or Test Net Connection PowerShell CMD-let to verify that these ports are reachable. Time synchronization is often the culprit when Kerberos fails. As we discussed earlier, clocks must be synchronized within 5 minutes. You can check time synchronization using w32tm/query/status to see the current time source and offset. If time is out of sync, force synchronization with w32tm/resync and verify that the Windows time service is running and properly configured. On virtual machines, Check that VMware Tools or Hyper-V Integration Services is properly configured for time synchronization. Service principal name issues are another common cause of Kerberos failures. If an SPN is missing, duplicate, or registered on the wrong account, authentication will fail. Use set SPN queue to query for SPNs. For example, set SPN queue http://webserver.corp.contoso.com will show if the SPN exists and which account owns it. Use set SPNL account name to list all SPNs registered to a specific account. If you find duplicate SPNs, remove the incorrect ones using set SPND. If SPNs are missing, register them using set SPNS. Always register SPNs on the account that the service actually runs under. Windows provides several tools for capturing and analyzing Kerberos traffic. The CLIST command shows the current Kerberos tickets in your credential cache. Run CLIST tickets to see all cached tickets, including their service names, validity periods, and flags. Run CLIST purge to clear the ticket cache, which forces the system to obtain fresh tickets on the next authentication attempt. This can resolve issues caused by stale or corrupted tickets. Event logs are invaluable for troubleshooting. You can enable Kerberos logging by creating or modifying registry values under HKLMSYSTEM current control set control LSA Kerberos parameters. Set log level to 1 to enable Kerberos event logging. Kerberos events will then appear in the system event log with source Kerberos. On domain controllers, review the security event log for authentication events with event IDs 4768 for TGT requests and 4769 for service ticket requests. Failures will show specific error codes indicating what went wrong. Network packet capture with Wireshark can provide deep insight into Kerberos exchanges. Capture traffic on port 88 and filter for Kerberos protocol. You can see the complete ASREQ, ASREP, TGSREQ, and TGSREP exchanges. While you can't decrypt the encrypted portions without the keys, you can verify that messages are being exchanged and identify error codes in responses. Common error codes include KDCERR preauth failed for wrong passwords, KDCERRC principal unknown for non-existent accounts, KDCERRS principal unknown for missing SPNs, and KRBAPERRSKEW for clock synchronization issues. For delegation issues, check that accounts are properly configured in Active Directory users and computers. Review the Delegation tab on Service Accounts to verify constrained delegation settings, and check the account is sensitive and cannot be delegated flag on user accounts that should not be delegated. Use Active Directory PowerShell CMD lets like get AD user and get AD service account to query MSDS allowed to delegate to and other delegation related attributes programmatically. Kerberos pre-authentication. Pre-authentication is a critical security mechanism in Kerberos that prevents offline password guessing attacks. To understand why pre-authentication is necessary, we need to consider what would happen without it. In the original Kerberos specification, a client could send an ASREQ to the KDC without proving they knew the password. The KDC would respond with an ASREP containing a TGT encrypted with the user's long-term key. An attacker could request ASREPs for any username and then attempt to decrypt them offline using a dictionary of possible passwords. If the decryption succeeded, they would know they had found the correct password. Pre-authentication solves this problem by requiring the client to prove they know the password before the KDC will issue any response. The most common form of pre-authentication is encrypted timestamp pre-authentication. When the client sends an ASREQ, it includes a timestamp encrypted with the user's long-term key. The KDC attempts to decrypt this timestamp using the key it has stored for that user. If decryption succeeds and the timestamp is current within the allowed clock skew window, the KDC knows the client possesses the correct password. Only then does the KDC issue an ASREP if the encrypted timestamp cannot be decrypted or is not current. The KDC rejects the request without revealing any information that could be used for offline attacks. The encrypted timestamp contains the current time in microsecond precision along with a sequence number. This microsecond precision ensures that even if an attacker captures a valid pre-authentication message, they cannot successfully replay it, as the timestamp will be stale by the time they attempt its use. The KDC maintains a replay cache of recently seen timestamps to detect and reject duplicate authentication attempts. This prevents an attacker from capturing a valid ASREQ and replaying it to gain authentication. In Active Directory, pre-authentication is enabled by default for all user accounts. However, administrators can disable it on individual accounts through the user account control flags. The setting is called "Do not require Kerberos pre-authentication" and should almost never be enabled. Accounts with pre-authentication disabled are vulnerable to ASREP roasting attacks, where attackers request ASREPs for those accounts and attempt to crack the passwords offline. Security scanning tools specifically look for accounts with pre-authentication disabled as they represent high-value targets. There are legitimate scenarios where pre-authentication might need to be disabled, such as for compatibility with very old Kerberos implementations, but these should be rare and carefully evaluated. Alternative forms of pre-authentication exist beyond encrypted timestamps. Smart card authentication uses public key cryptography for pre-authentication, where the client signs a challenge with their private key stored on the smart card. The KDC verifies the signature using the corresponding public key stored in the user's certificate. This provides strong authentication without requiring password-based pre-authentication. Fast armoring, which we discussed earlier, also modifies the pre-authentication exchange by wrapping it in an encrypted tunnel, providing additional protection against attacks. Modern Kerberos implementations support multiple pre-authentication types, and the client and KDC negotiate which type to use during the authentication exchange. Kerberos and NTLM fallback. While Kerberos is the preferred authentication protocol in Windows environments, NTLM, the older NT-LAN Manager protocol, still exists for backward compatibility. Understanding when and why the system falls back from Kerberos to NTLM is important for both security and troubleshooting. NTLM is less secure than Kerberos and doesn't provide the same single sign-on capabilities, so administrators should work to eliminate NTLM usage where possible. The system attempts Kerberos authentication first in most scenarios. If Kerberos fails for any reason, Windows automatically falls back to NTLM without user intervention. This transparent fallback means that authentication usually succeeds even when Kerberos is broken, but it also means that Kerberos problems can go unnoticed because NTLM masks them. Several conditions trigger fallback to NTLM. If the client cannot locate a domain controller, Kerberos fails because there's no KDC to issue tickets. If the requested service does not have a registered SPN, the client cannot request a Kerberos ticket for that service. If clock skew exceeds the maximum tolerance, Kerberos timestamp validation fails. If the client is authenticating using an IP address instead of a hostname, SPNs cannot be constructed properly because SPNs require DNS names. NTLM authentication works fundamentally differently from Kerberos. With NTLM, the client first sends their username to the server. The server then generates a random challenge and sends it back to the client. The client encrypts this challenge using a hash of their password and sends the encrypted challenge back to the server. Next, the server contacts a domain controller, providing the username and the encrypted challenge, and requests verification. The domain controller looks up the user's password hash, encrypts the same challenge using that hash, and compares the result to what the client sent. If these match, the authentication succeeds. This process means the server must contact a domain controller for every NTLM authentication. In contrast, with Kerberos, the server can validate tickets locally using its own key. Organizations should work to disable NTLM to improve security. NTLM is vulnerable to pass-the-hash attacks, where an attacker who obtains a password hash can authenticate without knowing the actual password. NTLM also lacks mutual authentication, so clients cannot verify the server's identity. To disable NTLM, you must first identify where it is still being used. Windows provides audit events that log NTLM usage. By enabling NTLM auditing through group policy, you can identify which systems and applications are still using NTLM. Common sources include applications that authenticate using IP addresses, older applications that do not support Kerberos, and systems accessing resources through load balancers or proxies that do not properly handle Kerberos. Kerberos encryption types and cryptographic agility. Over the years, Kerberos has supported various encryption algorithms, evolving as older algorithms became weak and newer, stronger algorithms were developed. Understanding the encryption types available and how to manage them is crucial for maintaining a secure Kerberos environment. The choice of encryption type affects both security strength and compatibility with different systems. The original Kerberos implementations used DES, data encryption standard, with 56-bit keys. DES was considered secure when it was first adopted, but advances in computing power made it vulnerable to brute force attacks. By the late 1990s, DES could be broken in days or hours with dedicated hardware. Microsoft introduced RC4 HMAC as an alternative, using the RC4 stream cipher with 128-bit keys. While stronger than DES, RC4 has known weaknesses and is no longer considered secure by modern standards. Security researchers have demonstrated practical attacks against RC4 in various contexts. Modern Kerberos implementations use AES, the Advanced Encryption Standard, which is currently the gold standard for symmetric encryption. Windows supports two AES variants: AES 128 CTS HMAC SHA 196 with 128-bit keys, and AES 256 CTS HMAC SHA 196 with 256-bit keys. Both are considered secure by current standards, with AES 256 providing an additional margin of security. The CTS designation stands for cipher text stealing, a mode of operation that allows encryption of messages that are not exact multiples of the block size, without needing padding. The HMAC SHA 196 portion provides integrity protection using a keyed hash, ensuring encrypted data has not been tampered with. Each principal in Kerberos can support multiple encryption types simultaneously, and the encryption type for each ticket is negotiated during the authentication exchange. The client indicates which encryption types it supports in the ASREQ, and the KDC chooses the strongest mutually supported type. Different tickets in the same authentication session might use different encryption types. For example, the TGT might use AES 256 while a service ticket uses AES 128 if the target service only supports AES 128. This negotiation provides cryptographic agility, allowing the environment to gradually upgrade encryption types without breaking compatibility. Kerberos protocol transitions and S4U2 self. Protocol transition is a Kerberos feature that allows services to obtain Kerberos credentials for users who authenticated through non-Kerberos mechanisms. This capability is essential in modern hybrid environments where users might authenticate using various protocols such as forms-based authentication, certificate authentication, or federated identity protocols like SAML or OpenID Connect. Protocol transition bridges these authentication methods with Kerberos protected back-end resources. The mechanism for protocol transition is the S4U2 self-extension we discussed earlier. In this context, we are focusing on its use for converting non-Kerberos authentication to Kerberos tickets. Imagine a web application that uses forms-based authentication. A user enters their username and password into a web form. The application then validates these credentials against Active Directory using an LDAP bind or another mechanism. At this point, The web application knows the user is authenticated, but it does not have a Kerberos ticket for them. If the web application needs to access a back-end database or file share on behalf of the user, it requires a way to perform Kerberos authentication using the user's identity. With protocol transition enabled, the web application can use S4U2 Self to request a service ticket from the KDC on behalf of the user. The application authenticates to the KDC using its own service account credentials and includes the user's principal name in a PA for user field in the TGSREQ. The application is essentially asserting, I have authenticated this user through another means, and I need a Kerberos ticket for them. The KDC validates that the service account is trusted for protocol transition, then issues a forwardable service ticket to the requesting service with the specified user as the client principal. For protocol transition to work, the service account must be configured with specific permissions in Active Directory. The account needs the trusted to authenticate for delegation right, also known as protocol transition. This is configured through the Delegation tab in the Account Properties in Active Directory Users and Computers, or through the Trusted to Auth for Delegation flag in the User Account Control attribute. Additionally, the service account typically needs constrained delegation configured to specify which back-end services it can access on behalf of users. The combination of protocol transition and constrained delegation provides a secure way to handle authentication in multi-tier applications. Security considerations for protocol transition are important. When a service is trusted for protocol transition, it can obtain Kerberos tickets for any user by simply providing their username. This is extremely powerful and potentially dangerous if misused. If an attacker compromises a service account trusted for protocol transition, they can impersonate any user in the domain. For this reason, accounts trusted for protocol transition should be carefully secured and monitored. Use strong passwords or managed service accounts. Implement least privilege by limiting which services the account can delegate to, monitor for unusual patterns of ticket requests, and regularly audit which accounts have protocol transition enabled. The account should not be used for any purpose other than running the specific service that requires it. Kerberos and Azure Active Directory. With the increasing adoption of cloud services, understanding how Kerberos integrates with Azure Active Directory is becoming essential. Azure AD is Microsoft's cloud-based identity service. While it primarily uses modern authentication protocols for cloud applications, for example, OAuth 2.0 and OpenID Connect, it still needs to interoperate with on-premises Active Directory environments that use Kerberos. Several integration patterns exist to bridge these worlds. The most common integration scenario is the hybrid identity model, where an organization synchronizes their on-premises Active Directory to Azure AD using Azure AD Connect. Users have accounts in both environments, and the password hashes are synchronized from on-premises to the cloud. When a user authenticates to cloud services, Azure AD can validate their credentials. However, when that same user accesses on-premises resources, they need to use Kerberos authentication. The Seamless Single Sign-On, or Seamless SSO, feature enables users to automatically authenticate to on-premises resources when using Azure AD joint devices without having to enter credentials again. Seamless SSO works by creating a special computer account in the on-premises Active Directory named AZUREADSSOACC. This account represents Azure AD in the on-premises environment. When a user authenticates to Azure AD and then tries to access an on-premises resource, their browser is redirected to the on-premises Active Directory. The browser, configured through group policy or other means, recognizes this as an intranet site and automatically attempts Kerberos authentication. The client requests a TGT from the on-premises KDC, but instead of using the user's password to decrypt the ASREP, it uses a key that was established during the seamless SSO setup. This allows the cloud-authenticated user to obtain on-premises Kerberos tickets without re-entering credentials. Another integration pattern is Azure AD Domain Services, which provides managed Active Directory domain services in Azure. This is useful for lift and shift migrations of applications to Azure that require domain join, group policy, LDAP, or Kerberos authentication. Azure AD Domain Services creates a managed Active Directory forest in Azure and synchronizes users and groups from your Azure AD tenant. Applications running in Azure can join this managed domain and use traditional authentication protocols. The managed domain services include fully functional KDCs that issue Kerberos tickets, allowing cloud-based applications to use Kerberos without maintaining on-premises domain controllers. However, this creates a separate forest from your on-premises environment, so trusts and cross-forest authentication considerations apply if you need resources to communicate between environments. Windows Hello for Business is another technology that affects Kerberos authentication in hybrid environments. Instead of using passwords, Windows Hello for Business uses asymmetric key pairs for authentication. When a user enrolls in Windows Hello, a key pair is generated, and the private key is bound to the device's TPM chip. During authentication, the user unlocks the private key using a PIN or biometric, and the system uses it to sign a challenge. In hybrid deployments, Windows Hello can request Kerberos tickets for on-premises resources. The system uses a certificate-based authentication mechanism to request a TGT from the on-premises KDC. The KDC validates the certificate and issues a TGT, allowing the user to access on-premises resources without ever transmitting or using a password. This provides significantly stronger security than password-based Kerberos authentication while maintaining compatibility with existing Kerberos protected resources. Kerberos Performance Optimization. While Kerberos is efficient, in large environments with thousands or tens of thousands of users, authentication performance can become a concern. Understanding the performance characteristics of Kerberos and how to optimize them ensures that authentication does not become a bottleneck. Several factors affect Kerberos performance, and several optimization strategies can be employed. Domain controller capacity is the primary factor in Kerberos performance. Every authentication request is processed by a KDC, which is a domain controller. The KDC must perform cryptographic operations to validate pre-authentication data, generate session keys, and encrypt tickets. These operations are CPU-intensive. In a large environment, domain controllers can process thousands of authentication requests per second. If domain controllers are under-provisioned or overloaded, authentication latency increases. Users experience slow logons, delayed service access, and timeout errors. Monitoring domain controller CPU and memory utilization is essential. If domain controllers consistently run at high CPU utilization, especially during peak hours like morning logons, you need additional domain controllers to distribute the load. The number and placement of domain controllers affects authentication performance. Users should authenticate to domain controllers on the same local network segment to minimize network latency. In environments with multiple sites connected by WAN links, each site should have at least one domain controller. Active Directory site configuration ensures clients authenticate to local domain controllers. If site links are not properly configured, clients might authenticate to domain controllers across slow WAN links, adding significant latency. Use the nltest/ds-getDC command to verify which domain controller a client is using and ensure it is a local one. If clients are authenticating to remote domain controllers, review your Active Directory sites and services configuration. Ticket lifetime configuration affects the frequency of KDC requests. Longer ticket lifetimes mean that tickets are reused more and refreshed less frequently, which reduces KDC load. However, longer lifetimes increase security risk if tickets are compromised. The default 10-hour TGT lifetime and 7-day renewable lifetime provide a good balance. Service tickets are typically cached and reused until they expire. If you are experiencing high KDC load, increasing ticket lifetimes can help, but you must evaluate the security implications. Conversely, If security is paramount and you want to limit the window of vulnerability for stolen tickets, shorter lifetimes are appropriate, though this increases KDC load. Network optimization also improves Kerberos performance. Kerberos uses UDP port 88 by default for authentication requests. UDP is connectionless and has lower overhead than TCP, making it faster for small messages. However, if tickets become too large, they exceed the UDP packet size limit, and the protocol falls back to TCP, which is slower. Ticket size grows with the amount of authorization data, primarily the user's group memberships. Users who are members of many groups have larger tickets. If tickets exceed about 1400 bytes, UDP fragmentation occurs, and if they exceed the maximum UDP message size configured in Kerberos, typically 2000 bytes, TCP is used instead. You can increase the maximum UDP message size through registry settings to avoid TCP fallback. The registry key is HKLM/SYSTEM/ current control set /control /LSA /Kerberos /parameters with value max packet size. However, very large UDP packets can cause network issues, so this should be done carefully. Alternatively, reduce authorization data size by minimizing user group memberships and using group nesting strategically. Caching at the client side is crucial for performance. Windows aggressively caches Kerberos tickets, reusing them until expiry. This means that once a user has authenticated to a service, subsequent accesses are nearly instantaneous because no KDC interaction is needed. Ensure that applications are designed to take advantage of this caching. Applications should request tickets once and reuse them rather than requesting new tickets for every operation. Some poorly designed applications or services might purge tickets unnecessarily or fail to cache them properly, causing excessive KDC load. Monitor for applications that generate unusual volumes of ticket requests. Finally, consider read-only domain controllers in scenarios where domain controllers are deployed in less secure locations. Future of Kerberos. In conclusion, Kerberos has proven to be remarkably resilient and continues to be the backbone of enterprise authentication decades after its initial development. However, the authentication landscape is evolving, and it is worth considering how Kerberos fits into the future of identity and access management. Modern authentication protocols like OAuth 2.0, OpenID Connect, and SAML are increasingly prevalent, particularly for web and cloud applications. These protocols were designed for internet-scale authentication and offer features like federated identity, delegated authorization, and mobile-friendly authentication flows that Kerberos does not natively support. Despite the rise of modern protocols, Kerberos remains essential in enterprise environments. Many critical systems and applications rely on Kerberos and will continue to do so for the foreseeable future. Windows authentication, Active Directory integrated applications, enterprise databases, file servers, and legacy systems all depend on Kerberos. Rather than replacing Kerberos, the trend is toward hybrid architectures that bridge Kerberos with modern protocols. Technologies like Azure AD with seamless SSO, Windows Hello for Business, and certificate-based authentication demonstrate how Kerberos can interoperate with newer authentication methods. Security improvements to Kerberos continue to be developed and deployed. Kerberos Armoring with FAST provides enhanced protection against offline attacks. Support for stronger encryption algorithms like AES ensures cryptographic strength keeps pace with computing capabilities. Public key cryptography integration through PKI-NIT allows smart cards and certificates to be used with Kerberos. Compound authentication binds user and device identity together. Resource-based constrained delegation provides more flexible and secure delegation models. These enhancements ensure that Kerberos remains secure even as attack techniques evolve. For organizations managing Kerberos environments, we recommend several best practices. First, maintain strong, fundamental security hygiene. Enforce complex passwords. Use managed service accounts. Regularly rotate service account passwords, and implement least privilege. Second, eliminate weak encryption types by disabling RC4 and DES, enforcing AES-only authentication where possible. Third, disable NTLM to the extent possible to reduce the attack surface. Fourth, implement comprehensive monitoring by enabling detailed Kerberos auditing, centralizing logs in a CIM, establishing baselines, and alerting on anomalies. Fifth, protect privileged accounts by marking them as sensitive and as unable to be delegated, implementing credential guard, and using privileged access workstations. Sixth, maintain proper infrastructure by ensuring adequate domain controller capacity, configuring Active Directory sites correctly, and maintaining time synchronization. Finally, stay current with security updates and patches. Thank you for your attendance. Please consider subscribing to the channel and liking this video.